Hello, welcome to video 46 in the lecture Advanced Mathematic Modeling. So in the last lecture I introduced the random walks in 2 dimensions, and in this video we're going to explore a little bit the properties of these random walks. So we move to a new slide here. So first let's start again with the definition. So we have the random walk, the position of the walker at time t is the sum, the vector sum of the increments from I equal 1 to t. And now again the problem is, what are the moments of the position? So we could first ask, so what is the first moment of the position, so the expectation of the position. So that's, and this is the same calculation now we did for the one-dimensional random walks. It's basically the same. We need the expectation of here the sum of the increments, and this is the expectation of the sum is the sum of the expectations of the increments I equal 1 to t. And now if we assume we have a stationary process, this expectation does not depend on time anymore, and then we have here t times the expectation of the increment. And so that's, we have basically the same formula as before. And if we have now basically that all increments have basically can go in all directions, so that the mean of the increments is 0, then the mean of the position will not move in time. And then we're interested in the deviations from 0, so we're interested in the second moment r squared. And so this is now the expectation of the sum of the increments times the sum of the increments. And again, it's the same formula, same thing that we had before, we just have the vector errors. So let's write this a bit more in detail. So we have here E1 plus E2 plus E3 plus and so on and so forth, multiplied by E1 plus E2 plus E3, and from all of this the expectation value. And then we can, as before, we can take out in this product the terms where we always multiply the same indices, the increments of the same indices, and this gives then t times the scalar product of an increment with itself, plus so the second moment of the increments. And then we have only the terms ei times ej, where I is not equal j. And so this is here the expectation of r square, and this is the expectation of r. And so these are the two major results, and they correspond directly to the results we had in one-dimensional random walks, with the difference that now here for the first moment we have a vector, we have a really orientation. So if we have the walk with a bias, for example, walk with a bias, if here this is not 0, and then we have to know what is this this vector. Maybe it's a vector which goes in this direction. the expected value of the increments. And now if we start a random walk, it will zigzag around. But eventually the position of the walker will follow the direction of the bias. So as we had before, a walk with a bias, but only now the bias has a directionality in space. And then, as usual, we can go in a coordinate system which moves with the bias, and then the remainder of this walk is then a walker with bias 0. So as usual, then we can always restrict us to a situation where this expectation of the increments is 0 if we go to this moving coordinate system, and then we're interested in the mean square displacement of the remaining movement. And then now what does this mean square displacement tell us? Mean square displacement in 2D random walk. So we have here again our two-dimensional plane. We start somewhere. Now we don't have bias. The walker goes around here, zigzags, whatever. And then we want to know, after a certain time, what is the radius, the typical distance r that the walker has done as a function of time. And now we see, so the mean square displacement, so we would need to now to take the square root of this. So that gives us the typical size of your circle that the random walker will have crossed. And then we see this again goes with the square root of time, and it depends now again on this autocovariance function. And now there comes now something new. The new thing is that again we have the directionality. So let's look what does, because here we need a scalar product. Scalar product of increments. So we have here in the correlation function or the covariance function, we have the product of the increment at time e, at time I, multiplied by the increment at time j, and this is the scalar product. And so you know the scalar product is given as the absolute value of ei multiplied by the absolute value of ej times the cosine of the angle between these two vectors. So if we have one increment ei, if this increment is this vector, and we have another increment ej, and then we have here the vector, the angle theta ij, and then the scalar product depends on the length, the absolute length of the two vectors, and then the cosine of this angle, which basically means when we look at this here, so we take an expectation value of such cosines of angles. And now why is this important? And first these angles are called the turning angles. Because turning angle, because like our walker was at some time going in this direction, and then later, at a later time, is going here in this direction, and so he has turned around this angle theta here. So these angles are the turning angles. And now the movement, if you now have more macroscopic individuals, if you don't have now our grain of pollen which is really randomly kicked around, you have the movement of an animal, it's not so strongly zigzagged. So a real movement of an animal is more like a smooth thing, where the movement could maybe be described by something like this. So this could be the movement of an ant or a bird. So it's like kind of a smooth, so very often it's kind of a smooth trajectory. And now if now we assume that this movement is even done with constant velocity, if the animal walks with constant velocity but just turns around, then we could say what's happening if we have a constant step length. Let's write it here. If we have a constant step length, so when we say the absolute value of the increments, it's some constant. We can set it to 1 here, but it could be some typical scale S. And then the randomness of the motion of the walk comes only due to the turnings or to the change of directionality. And so here in the covariance sum, this here, we don't need even the sum. We have here this covariance EI times EJ, then it's just the expectation of the cosine, it comes here from the scalar product of the turning angles. And so we are interested, if we sum up the expectation of the cosine of the turning angles, this gives us the memory of the process if the step lengths are of the same length. So why is this a memory? You know, the cosine is maximal as 1 if the turning angle is 0. So if we have two steps which go in the same direction, so both increments are in the same direction, then theta is 0 and we have a strong contribution. If theta is 180 degree and EJ goes in the opposite direction than EI, then the cosine is -1, and then we have a negative contribution to this here. So a movement which has persistence, which has a long memory, is a movement where the tetas are very small, so that we get here very strong contribution in this covariance function. And so what's now interested, or what we are interested is in the time dependence, how this function depends on the time distance I and j. And we are also interested what are the turning angles anyhow. So we are interested in the distribution of the turning angles. And so like when you do this, for example, for this small cellular organisms, the protozoans, or for larger animals like water fleas, the Daphnia, they have been studied a lot, and here you have the turning angles, and we look for the distribution. So now and then we obtain very often something like this. P of theta, the distribution of turning angles. So most of the time the turning angles are very small, so very often this distribution is symmetric, so turning to the right or clock side or counterclock side has the same probability. And but smaller turning angles are more frequent, more likely than big turning angles, so most of the time there's small turning, so this is a smooth trajectory. And it's also typical that this is not a round curve here, but we have here this pronounced peak. And so you could say this distribution decays here as exponential of the absolute value, but it's symmetric with positive and negative angles theta. And so, so like again, what does this mean? If we have here a movement at some time point, then we can extend this in the future at this time step and then see what was the turning of this animal. And then at this time step here, the animal then decided to move in this direction, and that would be a straight line, and then it turns again. And so now, so we get a very different picture of a random walk. So instead of this random walk where we at a certain position just add one increment, yeah, always a new increment, here we just we also add an increment, but the increment has always the same step length, and we are interested how does the trajectory turn around. This gives then more smooth trajectories. And so this distribution of turning angles very often can be fitted. So if we take the absolute value, and this very often goes proportional to an exponential distribution, e to minus the absolute value of the theta e divided by some constant kappa. So that's a good fit, but this of course depends on what kind of animal you're looking and what kind of scale you're looking. Of course, now the question is, if we have a smooth trajectory, the question of course is where do this points from? Do we really have a hopping thing? So we have really a step like a mammal going with two legs, and then this could be a single step. It could be also the position at the next day of an animal, or it could be that we just have a continuous curve and we just arbitrarily, as the modeler, put in here this equally sampling size and then just look for turning angles. So then these step lengths are artificial and just introduced by the analysis. So that then depends on where do the individual steps come from. And then this distribution of turning angles is not a constant or for the organism, but this depends on the chosen step length. So if we would take the same trajectory but sample it at larger step lengths, then we would get very different distribution of turning angles. That's something one should have to take into mind. And if we now follow up this idea, so now if we now have a real animal, and so we are entering also in movement of analysis of movements of animals, we enter the area of big data where we get more and more data. If you put small devices like GPS or geo trackers on animals, you can even do it nowadays with very small animals like birds, and then we get more and more information about the trajectories that animals do in the real landscape, and we can now, with something like this, with distribution of turning angles, with looking for biases here, for calculating mean square displacement, so we can start to describe the movement of animals. Does this animal in this motion has a typical direction? Is this a migrating bird which wants to go to north in summer? How straight is the line? Is it more twiggling, so it has a broad distribution? Is it more smooth? And does the animal move in a diffusive behavior where the mean square displacement goes proportional, increases to proportional to square root of time, or is it a super diffusive behavior where the animal is moving more in a kind of ballistic motion? And so all of this leads to the field of movement ecology, where we really try to find the distribution of the increments and the turning angles and the correlations to really describe the movement of real animals or certain species. And so here the random walk theory comes to an application where we take the walk serious, and it's not just an artifact to analyze random numbers. Yeah? And so that was this, and I want to repeat that basically the analysis of here the first moments, but also if you want to have the whole distribution function of this position, a lot of the theory that we develop for 1D random walks, very straightforward, can be translated to 2D random walks if we just take into account these aspects of directionality. Okay, thank you.